Welcome to the new era of video creation with Bao Z8. Today we will discuss optimizing a deep learning model for production use. How would you optimize a deep learning model for production use, especially in resource-constrained environments, e.g., mobile, edge devices? When deploying a deep learning model to production environments like mobile phones or edge devices, several constraints must be considered. These include compute resources, memory limits, power consumption, and the requirement for real-time inference. Edge devices often run on low-power CPUs or mobile GPUs, making it crucial to optimize models for efficiency. Model complexity is a significant factor in these environments. A complex model might perform well in terms of accuracy, but its size and computational demands might make it impractical for devices with limited storage and processing power. The challenge is to balance the high performance of deep models with the low resource footprint required by mobile and edge devices. Additionally, achieving low latency is essential for real-time tasks, and ensuring scalability allows models to handle increasing user requests without degrading performance. Understanding these constraints is critical to building production-ready models. Optimizing deep learning models for production involves a set of well-established techniques that reduce model size and improve inference efficiency without compromising accuracy too much. Model pruning removes redundant neurons or weights. By pruning the model, i.e., eliminating weights with small magnitudes, we can maintain accuracy while reducing both storage requirements and computation time. Quantization reduces the precision of the model's parameters from 32-bit floating point to 8-bit integers or even binary representations, significantly reducing memory usage and speeding up computation. This process can be done without much loss in performance if handled carefully. Knowledge distillation is the process of training a smaller model, the student, to approximate the output of a larger model, the teacher. This allows for faster inference while maintaining much of the teacher model's accuracy. Sparse models activate only a subset of neurons or weights during each forward pass, reducing computation time and energy consumption during inference, especially on edge devices. Choosing an appropriate model architecture is critical when deploying deep learning models on resource-constrained devices. There are several lightweight and efficient architectures designed specifically for such environments. MobileNet v2 and EfficientNet are popular choices for mobile and embedded systems. These models are designed to have fewer parameters and lower computational costs while maintaining competitive performance on tasks like image classification. SqueezeNet focuses on minimizing parameters without significantly affecting the model's accuracy. It uses techniques like FIRE modules to compress the number of parameters required. Tiny versions of popular models like ResNet for image recognition or BERT for text processing are pruned and optimized for smaller devices. These tiny versions perform well on tasks where a trade-off between accuracy and size is necessary. Neural Architecture Search, NAS, can help automatically search for the best model architecture for specific hardware constraints. NAS optimizes models by testing multiple architectures and selecting the one that offers the best trade-off between accuracy and efficiency. Efficient handling of data is crucial for optimizing deep learning models in resource-constrained environments. Edge-based preprocessing involves moving certain data preprocessing steps to the edge device itself, thereby reducing the computational load on servers and enabling faster data handling. For example, image resizing or filtering can be done on the device before sending data to the model. Data quantization involves reducing the precision of input data. For instance, you can use lower resolution images for model inference if the accuracy trade-off is acceptable for the task at hand. On-device caching stores the results of frequently processed data, like recent images or speech data, locally, reducing the need for the model to process the same data multiple times or make redundant calls to remote servers. This is particularly useful for repetitive tasks like speech recognition or object tracking. Data augmentation can be applied in real time on the edge device to generate additional training examples. This improves model generalization by making the model more robust to different scenarios without needing to send data to the cloud. Reducing latency is essential for real-time applications. There are several strategies to ensure that model inference is both fast and reliable. Model parallelism involves splitting the model across multiple devices, such as using multiple cores of a mobile CPU or distributing the load across multiple edge devices. This speeds up the processing and ensures that larger models can be run effectively in parallel. Asynchronous inference allows multiple tasks to run in parallel. While one part of the model is processing, other tasks can proceed without waiting for the entire inference process to complete. The early exit mechanism allows the model to exit early once it is confident in its output, thus reducing unnecessary computation and speeding up inference. Edge cloud collaboration enables a hybrid approach where heavier computations, like training, are offloaded to the cloud, while the edge device handles light inference tasks. This reduces the burden on the device and ensures optimal performance. To ensure deep learning models fit within the constraints of small devices, model compression techniques are applied to shrink their size and reduce their memory footprint. Weight sharing is a technique where different parts of the model share weights, thereby reducing the total number of unique weights that need to be stored. This can be done across different layers or groups of neurons. Factorization decomposes weight matrices into smaller, more efficient matrices, which reduces the overall computational cost during inference. Tensor decomposition, such as SVD, can compress high-dimensional tensors into lower-dimensional forms while maintaining the model's ability to perform well on the task. Finally, optimizing the model for specific hardware ensures that the model runs efficiently on different platforms. For example, mobile GPUs may benefit from certain types of compression over others. After optimizing the model, it's essential to measure its performance on resource-constrained devices. Key metrics include: inference time measures the time it takes for the model to process input data and provide a prediction. This is critical in real-time applications like speech recognition or object detection. Memory footprint is the total amount of memory the model consumes during inference. This is a crucial factor for devices with limited RAM and storage, like smartphones. Power consumption is another important factor when deploying models on battery-powered devices. Edge AI systems must be optimized for low power usage to ensure long battery life. Finally, evaluating the accuracy versus latency trade-off helps in determining the optimal model configuration. Sometimes it's acceptable to sacrifice a small amount of accuracy for faster performance. Finally, once the model is deployed, it's important to ensure that it remains effective over time. Model monitoring tracks performance metrics like accuracy, latency, and user feedback in real time to ensure the model meets its production goals. Continuous learning systems allow the model to adapt and improve based on incoming data. This is useful in environments where the data distribution may change over time. Gathering user feedback helps in identifying potential issues that were not previously captured during training or evaluation. Finally, regularly updating models based on new data or insights is critical for maintaining relevance and accuracy in production environments. Incorporating best practices is crucial when deploying deep learning models to production. Edge AI integration allows for a seamless combination of cloud and edge resources. By leveraging edge computing for fast local inference and cloud resources for heavy tasks like training, we can ensure optimal system performance. Establishing performance benchmarks ensures that the model meets real-time processing requirements and performs as expected across different devices and conditions. Security is paramount, especially when handling sensitive data on edge devices. Ensuring model integrity and data privacy is necessary to comply with privacy regulations. Finally, scalability allows models to handle increasing traffic loads as demand grows. Designing systems that can scale horizontally is essential for maintaining robust performance in high-demand environments. In conclusion, optimizing deep learning models for production in resource-constrained environments involves balancing accuracy, speed, and model size. Techniques like model compression and quantization are essential for making models lightweight and efficient without compromising on performance. Efficient data handling, preprocessing, and latency reduction strategies are key to enabling real-time performance. Edge cloud collaboration enables optimal resource usage by splitting tasks between local and remote devices. Continuous monitoring and regular model updates ensure the model remains effective as the environment evolves. Following these strategies will help you deploy high-performance models, even in challenging resource-constrained environments.